Okay guys, in this video we're going to kind of dive deeper into these different rules that we have in terms of where the electrons reside, following the off-ball, Pauli exclusion, and the Hund's rule. And the goal here is to apply these different rules to our orbitals. That way we are able to configure where the electrons are located. Okay, so first thing, this is the off-ball principle. All right, now the off-ball principle, if we look at it in terms of what it is, it tells us that electrons are going to occupy the lowest energy orbital first. Okay, so what that means to us is that electrons are always going to fill from low energy to high energy. Okay, now this image over here shows us our different energy levels, and it also shows us our different orbitals in those energy levels. So we have our first energy level, our second energy level, our third energy level, our fourth energy level. Okay. Here over here we have energy going up. So if we were filling electrons, we would first put electrons on the first energy level. Okay, and it would go into an S-shaped orbital. We call that the 1s. 1 meaning the level, and S meaning the shape of the type of orbital we have. Okay, we can put 2 electrons here because the S can hold 2. Now, on the second energy level, we now get a more complex energy level. So in the second energy level, we have both S-shaped orbitals and P-shaped orbitals. So we can put 2 more electrons on the 2s. And then remember, the P has 3 different orientations, the X, the Y, and Z orientation. So on the P orbital, we can actually put a total of 6 electrons, 2 in each orientation. Okay. Once we get to the third energy level, we get the S, the P, and the D shaped orbitals. Okay. But something weird starts happening. We notice that on the fourth energy level, we now get the S, the P, the D, and the F. Okay, so it actually takes to the fourth energy level before the F orbital even starts to exist. Okay, but the weird thing is the third energy level and the fourth energy level actually overlap each other. Okay, this continues. So in the fifth energy level, sixth energy level, and seventh energy level, all this continues, and we even get more overlap. Okay, now that's tough for us because if I'm filling electrons in and we're abiding by off-ball principle, we always want to fill from lowest to highest energy. So we got to fill the 1s, then the 2s, then the 2p, then the 3s, then the 3p. But in terms of energy, on the fourth energy level, the S-shaped orbital is actually slightly less energy than the third energy level's D-shaped orbital. Okay? So as a result, we get this overlap here. So before we can finish the third energy level, we actually had to start filling in the fourth. Okay, according to off-ball principle. So that's a trick that we have to deal with, and we'll have a pattern for you to show you how to do that. But just the key here is realizing that we always fill from low to high energy, and there is overlap here that we have to handle or deal with as we start to map out our electrons. Okay, that's our first rule. Second one, the Pauli exclusion principle. Okay, Pauli exclusion principle tells us that we can put a maximum of 2 electrons at any one orbital. Okay, we've been doing that already, but here's the rule behind it. Okay, we call these electron pairs, and you might think, wait a minute, how do 2 electrons pair up? They both are negatively charged. Wouldn't they want to get away from each other? And absolutely, they would normally. Okay, there's something else inside an electron called magnetic spin. So the electrons actually spin and create an opposite or opposing magnetic field. So when you have opposite magnetic fields from this spin, they actually attract each other. Okay, so even though their charge is the same, the opposing or opposite magnetic fields attracts, so then they pair up. So we actually will deal with electrons in pairs a lot in this class. Now, within this idea, or the Pauli exclusion principle, every orbital gets to hold 2 electrons. But remember, different orientations have different locations, so they can have their 2 electrons. So the S has 1 orbital, so it gets 2. The P has 3 different orientations, or essentially 3 different regions. We call them orientations of the orbitals, the px, py, pz. So it has 6 different electrons it can host. The D has 5 different orientations to it. So it's called the dxy, the dyz, the dxz, the dx squared minus y squared, and of course my favorite, the dz squared. It's kind of like my rapper name back in the day. I used to go by dz squared. I was kind of like a East Coast, kind of rapper that dealt with chemistry stuff. I don't do it anymore, but that was me, DZ squared. Anyway, because there's 5 different orientations here, we can get 10 electrons in that. And of course the F, I won't even give you their orientations. I don't even care if you know what they are. I don't even know what they are. But there's 7 of them, and that gives us a total of 14 electrons. Okay, so Pauli exclusion principle is the rules basically on 2 per orbital orientation. Now Hund's rule tells us that as you are filling electrons, you want to go from low to high energy, maximum of 2 electrons. Now Hund, what it adds in is that you want to make sure you fill in the most stable configuration possible. So as you're filling, if you have choices on where you put electrons, you do it in terms of increasing stability. Okay. What that really comes down to is when you're in a P-shaped orbital or a D-shaped orbital, okay, and you have 3 orientations or 5 orientations, where do you put the electrons? Do you put them all in? Do you start to pair them up right away, or do you actually put them like half fill them and so forth? Okay, so if we take a look, sometimes you will see orbital box diagramming done. Now, I'm not going to ask you to do this in class ever, but it is a pretty good visual in terms of how we deal with that. Okay, so we're going to jump out here, and we're actually going to go to this. It's called a dynamic periodic table for us to take a look at. And in the dynamic periodic table, there's this thing called orbitals. So if I click on that, it shows this orbital box diagram and the different elements. Okay, so right now we're on hydrogen. Hydrogen has 1 electron. Oh, I moved to helium, so I'm on hydrogen. Hydrogen has 1 electron, and it's going to sit in its 1s orbital. Okay, it's going to look like this. Okay, if I go down to tin and I click on tin, okay, tin has 50 electrons, and they're going to fill in all sorts of different types of the 1s, the 2s, the 2p, the 3s, and so forth and so on. And for tin, its most stable configuration is to fill this 5s, the 4d, and then it's going to fill 1 electron. The arrows represent electrons. Sorry, I should have said that before. These arrows inside here represent electrons. It's going to put 1 of its 2 remaining electrons in each of these boxes. Okay. So if we go back and look at the rule on this, okay, hydrogen is pretty easy, 1 electron. Helium has 2 electrons. Lithium has 3 electrons. Beryllium, 4 electrons. We get to boron, and it has 5 electrons. So of course, this pattern of putting 2 in, put 2 in, and then go to 1, that's the only way you could do it. But as soon as we get to carbon, the question becomes, do we pair up that first box? So do we put the electron here, or do we move over here and put it in here instead? Okay, so let's see what the right answer is. We click on carbon, and we notice that after it fills the px, it goes to the py. We go to nitrogen that has 7 electrons. It puts its last electron in the pz. So the most stable configuration in terms of filling is to put 1 electron in each orbital before you pair them up. Okay, and that's basically what Hund's rule does for us. It tells us is as we are filling, the most stable manner is to half fill each orbital first, and then go back and fill them. Okay. A repercussion of this rule is the fact that when you're looking at electron configurations, that you actually have these areas of stability. So certain elements are more stable than others. Okay. So when we talk about being more stable, if we can jump back to this periodic table, okay, things that have full boxes or half full boxes are more stable. So if we look, helium, for example, has a full 1s. Beryllium also has a full 1s and 2s. Magnesium, everything is full. Calcium, everything is full. Okay, so these elements here would be more stable than their neighbors who don't have it full. Okay, over here, zinc, everything inside of zinc is full. Cadmium, everything is full. Mercury, everything is full. Okay, so purely on stability, these are more stable elements compared to something in here like nickel. Less stable because it has some full, some half full. It's not as stable of an element. Okay, you want to have things that are like manganese, where it's either half full across the board, or like zinc, where it's completely full across the board. Those are areas of stability. Okay, and that's one of the repercussions of Hund's rule is that having things completely half full or completely full actually creates stability within our different atoms. Now, if we're looking at the periodic table, it can actually guide us and help us determine where electrons are being located. Okay, so inside of here we have what I call the s block. So these 2 rows are our s orbitals. Our d block is in here, our p block is in here, and our f block is here. So as you're trying to look at location of electrons and where are they filling, okay, we can actually use the periodic table to map it out and help guide us do that. Okay, in our next video, we're actually going to go deeper into this idea of using the periodic table to guide us and taking these 3 rules and then applying them and actually configuring or writing out the entire pattern of where the electrons are located. We call that electron configuration. Thanks, guys.